So let's start with an amazing AI for Research track. Big thanks goes to Lithuanian RDI liaison office Lino for partnering on building this track. Have you ever considered that sometimes the harder part is to identify the problem rather than finding a solution? Every day we spend generous time on processing the information. What if AI could do this job for us effortlessly? In fact, it can, and it does it already. It is used in interpretable prediction of protein binding sites with geometric deep learning. It helps in crossing the barriers between languages and building a data-driven information hub for sustainable urban mobility. AI could even be adjusted for cultural heritage monitoring. Let's begin with a topic about AI in Industry 4.0 from Dr. Robert Kadikis, Head of Robotics and Machine Perception Laboratory. Dr. Robert is a senior researcher and a head of Robotics and Machine Perception Laboratory at Institute of Electronics and Computer Science in Latvia, where he works for 10 years. He has a PhD in electronics since 2018 and is also a member of EDI's Scientific Council. The main research areas are artificial intelligence and computer vision and their applications in intelligent transportation systems, self-driving cars and drones, biomedicine, and Industry 4.0. Research interests include object detection, image segmentation, generative models, and bio-inspired AI. Good day to you, Robert.
Hello, good day.
Doctor, it's an honor to have you opening our stage. How is your mood? How are you feeling? Are you ready to kick off our stage?
Yes, it's great to be here. It's a good day today, so I'm ready. Let's begin.
Amazing. So, the virtual stage is now yours.
Thank you. So, once again, hello everyone. I'm Robert Kadikis from EDI. It's a research institute in Riga, Latvia, as you already heard. Today I will talk mostly about AI and robotics, but it's not only thing that EDI is doing. So just for quick introduction, we have 5 main research areas. First is extremely precise event timing. Here we are known for our very precise timers. They are used in satellite ranging stations, which are shooting lasers to satellites and measuring precise time the laser comes back, so they know precise distance to these satellites. Then the second main research area is remote sensing and space data processing. So we can take images from the same satellites or maybe planes or drones and process this image to discover, for example, what kind and how many this kind of trees are in woods and so on. And then, of course, robotics and machine perception, signal processing and embedded intelligence. That is what's my topic of today's speech. And the 5 research we are doing is smart sensors and Internet of Things. And we apply all this research mainly in 4 areas, which is health, space, mobility, and industry. So today it's Industry Day. This is our laboratory with an industrial robot. We have made it capable to decide which object to take from a random pile, classify this object in different classes, and then manipulate it and put it where this type of object needs to go. Of course, robots in industry, it's nothing new. There are plenty of robots in industries that are doing different things, but those robots usually are not smart robots. They are pre-programmed to do specifically exact things, go exact trajectories, and manipulate exact known objects. So in this video, we see a robot which is fast, it is precise, but if something changes in its environment, it goes boom. Smart robots are the robots that can adapt to their environment. They have perception, they can understand that something has changed, and they can change their actions based on the environment. And this is one of the technologies that 4th industrial revolution is providing, or which is based on. So it includes artificial intelligence, big data, connected robots, and so on. So we see that robots will do more complicated things in industry that are used to need human labor to do that. At EDI, we're usually doing this research in research projects, and this robotic field is done in three Horizon Europe projects. First of them is AI for DI, which is artificial intelligence for digitizing industry. So very straightforward, the connection with industry and this project. Usually these are large projects with many partners, like in this one, there are 40 partners from different countries. So the aim of such project is very big. We would like to strengthen and expand AI usage in European industry and digitization project. But of course, we as a smaller partner usually are doing more specific things. And for example, with several partners of this project, we are working on this demonstrator of a smart robot. Smart, what makes it smart? It's first, it's capable to see the environment, so perceive what's happening. If something changes, it can change its actions. Also, partners are working on touch sensors, so the robot can actually feel that someone is touching it, or maybe what it has grasped, so it can feel how strongly it is doing that. Other partners are working to make the robot more easier to interact with humans, so they are working on gesture recognition, so you can control the robot very intuitively just with hand gestures. And of course, we also like to put all this processing on edge, so the processing is not happening on servers, it's not happening on some cloud, but it happens on the robot itself or very close to the robot on specific chips like system on chip or FPGAs, which is also what we at DI are doing, embedding these algorithms on these chips. Then another example of a project, it's VISTA, it's vision identification with this sensing technology and key applications. The big picture is there are partners that are developing different 3D sensors, so for short range, for long range, like LiDARs or 3D cameras, depth cameras. And there are other partners that are demonstrating the use of these technologies in different fields. And EDI, of course, is doing the Industry 4.0 demonstrator. So what we do here, we take our smart robot, which you already saw we're developing in different projects, and we try to apply it to a waste sorting problem at waste sorting plants, where one needs to sort different kinds of plastic bottles into different bins, because not all plastics are similarly valuable. And as we've seen in waste sorting plants, that there are many robots that are already doing the sorting, but there are some very difficult lines, like one is this GIF, where still human labor is needed for this dangerous task. And for example, there's another Horizon project. Once again, the main ambition is very big, bring the latest research into industry. And EDI here is working on a demonstrator that is capable to take different bottles from different cases, from different boxes, and put them into sockets. And also, of course, we're very interested that this robot can adapt to new products, to new types of bottles, to new type of sockets. So this was maybe I would say the motivation, what we want to do. So now I will talk more about how we're actually doing that. So it begins with perception. We add cameras to the robot. These are usual cameras, or these are depth cameras that give us 3D information. We also add sometimes proximity sensors, and we add these cameras either over the robot and these problems that we want to solve, or on the robot itself. And also, as you can see here, there are small cameras, cheap cameras, there are big cameras and expensive cameras. And what we're sometimes interested in is, can we get the same good results by using the small and cheap camera as with this expensive one? A few years ago, we would do these things by applying computer vision with handmade algorithms. So we would use some edge detectors, different segmentators, and do a lot of engineering to make this robot work good with these exact objects that we're using here. But of course, when something changes in your production and you change the object, there's a lot of engineering needed to be done to once again make this robot work good with the new objects. So for the last few years, we usually are applying machine learning here, as probably most who are doing something like that is doing. And the usual tasks we are solving with machine learning is either object detection, when it's enough for us to just get bounding boxes around the objects to see where the robot can take this object, or we're doing image segmentation, so we get more precise boundaries of the objects if it's needed, for example, not to use a grasping hand to take this object. And usually we begin by taking already known popular frameworks and known neural network models like YOLO or Mask RCNN. They usually have pre-trained networks already on the internet, so you can take these pre-trained networks and fine-tune it on your problem, and usually you already have quite a workable result. But of course, as we're a research institute, we're also interested in more exotic architectures, so sometimes we try something new just to see maybe there is some relevant improvement for this task. Okay, but since it's machine learning, usually it's supervised machine learning, so it means we need a training data to train these algorithms to detect or segment images. To get this training data, well, one way is to manually label a lot of data, like you see here on the slide. There's some person going through thousands and thousands of images and drawing bounding boxes around objects that the robot could potentially take. So it's quite boring manual process. And of course, again, if you change your objects or lighting changes in your production lines, then this has to be done once again with new objects or with new environment situation. And what we're very interested is in changing this thing, or how can we just do this without data labeling? How can we alleviate this process? And one of our main research area right now is using synthetic data to train these neural networks. For example, here with our partners is a simulator which can simulate infinity examples of different piles using different objects. So we can generate we can generate a lot of data, a lot of images without manually labeling them, because since it's in simulators, all coordinates which we would use for annotations are already known in the computer. Here we also use the things that the simulators or game engines or 3D animation software is improving, so the realism is also improving. But one interesting thing that we do here is if you want to add new objects, you need to create a 3D model of this object. Sometimes it's not so easy, the object is complicated, and if we would like for everyone to be able to add new objects, then if they don't know how to create 3D models, it could be a problem. So one thing we're doing here is approaching it with putting a 3D sensor on a robotic arm, putting an object on a table, and letting robotic arm go around this object with camera, take several pictures from several sides, and then combining these pictures into a 3D object, which we can then automatically use in these simulations. And like in this image, which you can see here now, the bottles are modeled in 3D software, but these cans, metallic cans, are actually scanned with our approach. But then again, the big question usually is, but how actually real lifelike is this these 3D images? And to make them even more lifelike, we are currently interested in image translation approaches, which could translate like our synthetic generated images into something more lifelike. And here, the technology that's very fascinating for us is cycle gun and similar approaches, which, for example, could in literature translate images of zebras into horses or vice versa, by not changing anything else, just the animal, just the textures of the animal. Maybe very well-known examples of this similar technology are deepfakes, where there are faces that are changed for different people, but there are quite a big potential to use such technologies for machine learning in creating data. So here we can see that we have an image of synthetic data, we have an image of real data, and by training the cycle guns, we can translate, if you will, from synthetic image to a translated image that is a little bit more lifelike. The positions of the objects is not changed, but we see the colors are more similar to the ones that are seen on real images. Of course, there are some glitches still, but that's why this is ongoing research. And here is another example where we combine real images with simulation in physics simulators. For example, here we take several pictures of our objects of interest. Our algorithm automatically segments and cuts out these objects from the background. It's quite hard. We're dealing with transparent bottles, but then we use our simulator to simulate again different piles, like we're dropping here bottles, and then we once again put these real images from simulated piles onto real backgrounds, just to add this realism to data that we're using for training our object detectors or object image segmentators. And this is the same thing, just in picture form, in case the video doesn't run. But of course, in the end, there's always a question, but how well does it work? Can we replace all the real data with synthetic one and just be happy with that? Well, currently, all our approaches show that not yet. Synthetic data usually, of course, works worse than using real data for training. But what we have found is that when you combine synthetic and real data, you can even improve the accuracies of your detectors or segmentators over just using the real data. And of course, another good thing would be if you have small real data sets, you can add a lot of synthetic data set to this just to get the results that you could get with only real data, but in a big data set of the real data. But here we also research further how to combine this synthetic and real data to get the best results. So of course, we can just add images from one set to the other and use it all for training. It gets some improvement, but it's not the best way to do that, as we found out. For example, we can combine it in a little bit more interesting way. Like in this slide, there is a loss function that we are optimizing while training, but this loss function penalizes the network differently for the real and synthetic images. It's a coefficient alpha in these formulas, means that it's either more relying on real or more relying on synthetic data. And when changing this alpha, we see in figures that there can be found such alpha that is better than just using completely real or completely synthetic data. And it's not that it's alpha like 0.5. It's usually good to try to search for a good value to get this best optimal result. Oh yeah, okay, this is about our synthetic data approaches. We have several of them, and current papers are coming. And we usually have seen that there is quite interesting work after you have generated data just to decide which, how much to use for the best results. But then now we have the object detector or segmentator, and we want our robotic arm to actually take this object. Since this robotic arm is working in 3D environment, then it's not enough to give it a bounding box in 2D image. You also need to get the distance to the object in 3D. So that's why we're using depth cameras or 3D cameras, which give us depth maps where you can see that different colors mean how far the object is from the camera. But as you've seen, we have this application of bottle sorting, and these bottles sometimes are transparent. And transparent bottles, it turns out, are also transparent sometimes for a depth sensor. So here this animation shows if we put a depth sensor on robotic arm and look at our bottle from different angles, sometimes it completely disappears because it's transparent. So to deal with this problem, we attach another sensor to the robot, which is acoustic sensor. But before that, we also use object tracking algorithms. So when we have detected our object, we start to track it, and we move our robotic arm completely over this object. So tracking helps us to do this. And when this robotic arm is completely over the object, we use the acoustic sensor, similar to ones that were used in our cars for parking, but only this is very, very narrow beam sensor, and it's reflects from the object, and we can see precise distance to it. So this is just another problem that we encounter and solve, adding another perception capabilities. So, okay, we have detected and we have taken our object. Now we need to classify what kind of bottle it is, because talking with waste sorting plant managers, we saw that they're interested only in some kind of plastics, and some kind of plastics need to be thrown out, not so good for recycling, and so on. And so we saw a need to classify these bottles into 5 different classes. There are 4 different plastic classes, and then there's all opaque objects that are not so interesting for recycling. With cameras, it's not so easy to classify these objects, because sometimes these bottles look like identical to each other, but it's different plastic that is used to make them. So cameras is not enough. We add an additional sensor. For this case, it's a multispectral camera, or multispectral sensor that can get a lot of data points from different wavelengths and different materials reflect or absorb different wavelengths differently. So we see some examples of usual spectra of different plastics, and this is the data that we will use to classify our objects. But here, of course, it would be nice just to use machine learning and it works, but it turns out that best results could be we could get by using not only machine learning, but first using signal processing, different filtering approaches, and so on. Then we used principal component analysis to reduce features, because this multispectral sensor gives a lot of features. Not all of them are so important. And only then we use neural network to train these classifiers. But also here we use synthetic data approaches. We have here original approach which generates these spectra examples, and this whole combination gives the best results. So just one big conclusion for that was that signal processing is still very relevant, and machine learning haven't completely killed the need for something like that. Well, this was all about perception. We detected where the object is, but to actually take the object and then manipulate it, we also need to work on robot control. For now, we are writing these algorithms by hand. These algorithms include movement planning, trajectory generation, which avoids collisions with objects that we detect by cameras, and so on. To write all these control algorithms, we use robot operating system. It's just because it's very easy to work with different types of robots with this one system, because there are a lot of drivers there to work with this. But yeah, for now, as I said, we're doing this with manually creating different algorithms. Of course, sometimes we test them in simulations and we transfer them to the real robot. But going further, we see that here will be a lot of machine learning involved also in learning the control. So just to paint the picture that we see in the future, here, like a dream example that we see probably will be quite real, there is a production line. There are robots that are manipulating their objects. Then there comes some changes. For example, this factory wants to create new types of objects, or just maybe bottle is changed from one style to another, and the robot can't deal with it exactly. So we don't want the industry managers to call us, so we can come again and retrain this robot with all these algorithms. We want them to be able to do it by themselves. So what we see, there is like human who is usually supervising these robots. He comes with this new object that robots need to manipulate, shows it to robots' cameras, and shows what to do with this object just by hand, just taking the object, putting it where this object needs to go, and robot is learning from that. This is imitation learning. It's very dynamic research area right now, and as you see in this slide, it's written in green letters. So this green text is what we are very interested now and see as a very potentially interesting topic. So okay, this is imitation learning. Robot needs to learn how to do the same thing, but we would like this robot to learn just from few examples, not from thousands and thousands of examples as usually machine learning now do. So we're also interested in few-shot learning, which is also a very interesting research topic to look at. The learning of movements would happen in a simulation by reinforcement learning. It would be, of course, very interesting if real robot could just use reinforcement learning, where it tries to repeat the tasks humans show it, and if it's successful or more successful, it gets a reward. If not, it doesn't get a reward. But if we do that with a real robot, it's quite dangerous because there are unsuccessful attempts. It's quite long time taking long time because you can't simulate thousands of tries at once. You need to do it one by one. So that's why we're very interested in learning in simulations. Right now, reinforcement learning in different simulation environments already has showed very great results. The hard part is actually to bring those good results to the real life. So that's why here we see a term reality gap, how to transfer this, what you have learned in simulation to the real world. And of course, as you already saw in my presentation, we are doing some transfer using for perception, like you saw with cycle GANs, but similarly, they need to be done sim to real transfer for reinforcement learning algorithms for robot control. So this is also a very interesting thing to do. And all this green text is what we are now involved with. And now, when we have put all into this real robot, we're ready to put it. We're ready to give it the new object, and it can work with it. But of course, we're also interested to put all this perception and control algorithms on edge, because it means lower energy consumption, and it means more security if everything is done on the robot itself. So this is a cycle that we envision and that we're going towards. When we will solve all this green text, then probably industries would be left alone with this. They can do it and retrain and change all they want, and we can look towards the next big thing. So thank you very much. And I wish you a great conference.
Thank you so much, Doctor, for really interesting results that you shared during your presentation. I have a few questions from our audience and from myself. I'd like to start with the first one. Could you share your thoughts on how cross-countries or cross-organizations cooperation is pushing AI in Industry 4.0 development?
Yes, as I showed these European projects, there are in each of one of them are more than 20 partners from more than 10 countries or approximately that. So the push is there, the interest is there. There are a lot of topics in the calls of projects in the European level, which are oriented towards this robotics and industry, AI. So the push is there, the collaboration is already happening in full swing, and I think this is probably the big push that gives money to this research. So probably maybe, I don't know, but big part of research is happening just from this international push to do this.
We are now having a very wide audience watching at us, and maybe you are searching yourself for some partners that you'd like to mention.
Oh, yes, partners, it's always good. We're always searching for partners. And probably that's why good that I showed this last slide with the green text. So all the green parts is what we're interested in. We can't do that alone. Nobody can. So we're definitely interested in partners that are also interested in one of those green topics, so we can make some synergies and make bigger progress there.
Is that an invitation for people to ask you to connect on LinkedIn?
Sure, of course, yeah.
Okay. If we can step back a bit, what do you think? What's your personal opinion? What is the future of the companies that are not willing to embrace the AI in their processes currently? What do you think?
Well, there probably soon will not be such companies. Either they will embrace or probably will not be able to exist along these companies that embrace that. Of course, different kinds of companies have different time frames for that. If they are doing very, very complicated things that still is hard to automate, they maybe are not so, don't need to be so afraid right now or so interested in that. But each individual company needs to think about its processes, how easy it would be to automate, just to know if it's time to do that. And probably the best thing to do to decide what is easy to automate is just talk with some researchers in the area. They probably don't know as good what processes are happening in industry, but industry people probably don't know how easy what processes how easy are to automate. So just talking with researchers could already just give ideas where to look to go forward.
So the basic first steps should be to contact a local university or other organization that is working on automation, and just to come up and say, like, I'm interested in automating some of my processes in my company. Am I correct?
Yes, and there probably will be quite easy for them to tell, okay, no, this looks, no, not in 5 years, we can't do that. It's probably not so easy to automate, or, oh yes, we could do this in a few months or so. And of course, everything in between, but it will give very important information for industries, just talking for researchers. I guess I would say researchers are usually very open to give their opinions on such things.
Amazing. Doctor, you do see me on your screen now, right?
Yes.
I have a very short question for you, and I don't know what piece of the technology you have used, but I'd like you to meet someone, and I'd like to invite a person on the stage. Yes, you can join me here. And we can't understand what happened and how did you manage to appear in Vilnius in our broadcasting studio, but that was something very much unexpected. Dr. Roberts, I'd like you to meet our cameraman, Karolis.
Oh.
We do feel there's some similarities.
Yes.
And we obviously inspire you to connect on LinkedIn or Facebook and also speak to your parents. But that's maybe a very short joke for the kickoffing our track. Thank you, Karolis, for that. And dear doctor, thank you so much for your presentation. Thank you for opening our stage today, and good luck with your research.
Thank you. Nice to be here.
Ladies and gentlemen, that was Dr. Robert Kadikis, head of Robotics and Machine Perception Laboratory.